we will take chapter 9 and chapter 8. Okay. I will not cover all the material in these two chapters. Yeah, for example, this chapter 9, has more material than it is on the slide or in the notes. Same thing for chapter 8. We need to take the concept, the idea, and once we have the concept or the idea, we can easily expand on it. You can read the textbook, you can read the data sheet, if you want to use the additional features that we don't cover in the lectures. Okay, so regarding the proposals, I received your proposals and I went through them. All the proposals are approved, but I have a few things to say. The first thing is related to some of you. They mentioned that they are going to survey 6 papers or 5 papers. Some of you, 2 of you, I guess. I have no problem in that when it comes to writing your report. However, when you do the presentation, you need to make sure that you can present these papers in the allocated time. So if you have 6 papers, you can write about them in your report, but when it comes to presentation, you may focus on 2 or 3 of them and just shed some light on the remaining papers. Okay, what do we need from you in the report that you write and the presentation? Is to give us a general idea about the problem that is discussed in the papers and present 1 or 2 solutions that approached this problem in the papers that you selected. Okay, so I guess Muhammad, Saraira, I think Amal, they have 5 or 6 papers. لا يزن يمكن أنا ناسي والله بس I think Amal you have referenced 6 papers. صلحيني إذا أنا غلطان.
يس صح. عشان كانوا مرتبطين ببعض كثير فقلت بحطهم.
ما في مشكلة. You talk about them in your report, but try to pick the most
important ones.
I won't say the most important. I will say يعني الشيء the papers that you feel you are comfortable with. يعني أنت مرتاحة فيهم فهمتيهم كويس. They really address the problem in hand.
تمام.
اوكي نفس الكلام لاي حدا اخر عنده نفس النقطه هاي انه عنده اكثر من بيبر اكثر من 2 ما عندي مشكله. انت لما تكتب الريبورت you need to reference a lot of papers by the way, as many papers as you need, but your focus in terms of details should be about 2 or 3 papers as we said, but of course you might need to cite other references and other papers in your report. So this is the first thing. The second thing, which is something general actually, it is something related to how you present your work. Now most of you, they have put some effort in preparing their proposal in terms of formatting, in terms of layout, in terms of writing and language-wise. However, still, please put some effort in writing, in your presentation, because this is what sells. I know all of you have read or went through many papers and spent some time on this issue, so spend some time on writing the report, because if you don't present what you have understood, what you have taken from these papers and the resources, if you don't present it very well, it will look bad to you. Okay, so some of you, they did very well actually. The formatting, the layout, the language, it's obvious that they have put some effort in it. So this is very important, not for this course only, for all your master's courses and for your thesis. This is an exercise for you for the thesis when it comes to writing the thesis. Writing is not an easy task. It's not an easy job actually. It is very, very difficult and it is very, very critical, because if you can't present your work well, nobody will be interested in it. And this happens to me a lot when it comes to master thesis defense. When the students defend their thesis, in many occasions, they had poor writing. So when I read their thesis before I go to the defense, I feel like this is rubbish. Frankly speaking, this is rubbish. The student did not do anything. The student is not does not have enough understanding about his work. But when I go to the defense and the student starts to talk about his work and he answers the question and explains what he did, I discovered that he did a lot of work and it is significant. But that was not clear in his writing in the thesis. So writing is very important, and at the same time, it is difficult task. So please pay attention on that. And in order to be able to write, you need to read the books and the papers carefully in order to see how the scientific content is written. Okay, it is simple. It is usually a simple and plain language. You don't have metaphors and analogies in scientific writing. It is just plain, straightforward. You don't have to use complex words and expressions, but you need to be correct in terms of language. You need to be clear in the flow of ideas. This is very important. You need to know how to tell your story. Telling the story, which is your work, is very important. Okay, I always say it this way: your thesis is a story, and you need to tell this story in a very good and clear and enjoyable way. Okay. Okay. So that's what I wanted to say about the proposal. So all the proposals are approved. Go ahead, start working, reading the papers. And as I said, your report is not basically cut and paste from the papers that you are reading. You need to use your own language to put your own understanding, to criticize, to question the methodology in the papers, to question their assumptions, and so on. And this is, as I said, this is the way you do research. You read others' work, you understand the problem, and you try to build on others' work. You try to expand on others' work. You try to address issues that are not addressed in others' work. So this is basically how we do research. Yes, go ahead, Yazan. Yazan? All right, so you can start working on your term. تفضل.
كيف شوف مواضيعنا طيب يعني كأوفر أول يعني؟
سرايرة أنت يعني I think أنت خليني أتذكر أنت something related لل control للدي سي موتور والسynchronous موتور مظبوط؟
protection بالضبط.
هلا يعني أنت سويت بيك لبعض البيبرز. هلا معظمهم كما أذكر هم conference papers من ال IEEE, which is okay. But I would prefer, for example, in your case, إن يكون في عندك at least one journal paper. Usually, the journal papers they have more details, they have more depth in the topic. So the papers that you picked are okay, but if you can add to them a journal paper.
تمام دكتور تمام.
Okay. مروان.
عافية دكتور.
هلا مروان.
دكتور بدي اسالك هلا I saw انه انت حاطط بدك الريسيرش يكون IEEE format. Is this يعني mandatory or
هو mandatory عشان نتعود. يعني ال IEEE يعني template يعني it is very widely used بال IEEE conferences and the IEEE journals. So it is good to use it, and it is a very common يعني حتى even the non-IEEE conferences and non-IEEE journals, they also use somehow similar style. Okay.
Okay. And do you have a word count with the Kia, or are we allowed to?
لا ما هي التمبلت now, the template, if you open the template, it has certain specification for the formatting and the font size. You don't change that. For example, the titles of the sections should be of this font size. The text of the font size of the text, it is 10 point, for example.
Oh, yes, but I'm talking about the word count.
I don't care.
حط لنا الدكتور من 5 ل 8 صفحات.
Exactly. We have a limit, minimum 5 pages, maximum, I guess, 8. Yeah.
Okay.
So there is a minimum and maximum. And يعني, make sure that you do the writing with your own language. No copy and paste. Okay.
دكتور عادي بس سؤال بسيط عشان نبلش المحاضرة.
Yes, yes.
دكتور بصير لو مثلا البيبرز يعني احنا اللي يعني احنا اللي اخترناهم بالبروبوزال يعني اخذنا هيك اوفر فيو وكويك فيو عليهم، بس اذا بحالي يعني كمان ضفت يعني كمان ريفرنس او كمان بيبر او ممكن بدلت بيبرز.
It's okay ما في مشكلة. أنا بهمني التوبيك هلا، وزي ما حكيت يزن أنا when I asked for at least 2 papers, these are the 2 papers that the minimum number of papers that you need to give details about them, that you need to discuss. But
Yes.
you need to add, definitely you need to add other papers in terms of references, citation. When you talk about, let's say, the history of the problem, the motivation of the problem, most likely you will need to cite other papers.
Yes, تمام ان شاء الله.
Fatima, you did not submit a proposal, right? ولا فاطمة مش هون أصلاً؟
مش موجودة معنا طبعا.
let me see. أنا مش موجودة فاطمة بدها، أنا عم بحكي إنجليزي عشانها ومغلب حالي، بس هي مش كتير interested حسب الكورس. Anyway, she did not submit her proposal. So Fatma, if you see the video, please let's talk over the email. Let me know if you are going to submit a proposal. Okay. Tamam. Okay. Let's now move to our lecture. Our lecture is basically from chapter 9. We are going to cover another peripheral device that is usually found in many microcontrollers, medium range microcontrollers, advanced microcontrollers, which is serial communication interface, or the SCI peripheral or module. And basically, we will give a very quick introduction, about serial communication in general and asynchronous communication in specific. And as I said at the beginning of the lecture, this is the basic idea for any peripheral device inside the microcontroller. All what you need to know in order to use it is basically to understand how, in general, how this peripheral device, to understand the concepts of operation behind this peripheral, supported by this peripheral device, and then see how it is implemented in the microcontroller. So basically, we will start with an introduction, overview about serial communication, what is meant by serial communication, and so on. The second topic, I removed it actually, which is in red. So if you have the old version of the slides from the previous semester, this is removed. I removed it today before I uploaded the slides. So I will not talk about the standard, but basically this standard is one example on serial communication protocols. And this is actually, this was widely used in computer systems prior to the introduction of Ethernet and other networking technologies. So I will skip this, but it is already discussed in the textbook. Then we will go into the details of the serial communication interface that is available in the HCS12 microcontrollers. So basically, let's start with the introduction. And as we said, maybe at the beginning of the semester, we said that in general, the components that you may found in embedded systems are the computing core, the input devices, output devices, network interface, human interface, right? If you remember that figure where we have the core in the right at the middle, the computing core, and then we have different components around it. So one of these components that you may find in embedded systems is the network interface or communication interface, where the microcontroller can communicate with other components, with other systems. For example, you may have a weather station that is that resembles an embedded system, and this weather station is supposed to communicate with a remote server over 4G technology using mobile data, for example. So the microcontroller needs to support that, or at least need to be interfaceable to some device that can perform such communication. So basically, microcontrollers, depending on the application, they need to move data from and to some external devices, depending on the application. And in general, usually this is done using two approaches, either the parallel approach or the serial approach. And basically, in the parallel approach, the data that is to be communicated is sent out or received by the microcontroller in parallel, all at the same time. For example, the microcontroller can output 8 bits using some output port, some output port or parallel port, can read in 4 bits at a time. So this is called parallel communication, because if you are transferring 8 bits between the microcontroller and some other device, you do that in parallel. You transfer the bits of the data at the same time. So this requires a wire to be dedicated for each of the bits that is communicated. So if you are talking about transferring 8 bits, the microcontroller has to use 8 output pins and 8 wires to transfer this data. Or the same thing, if it is receiving 8 bits, then it has to use 8 pins. In other words, let's say it has to use one whole port, like port A in our case, or port B, which are 8 bits to receive the data. So this is simple approach. It is fast because it is a parallel operation, but it is expensive. It is expensive in terms of the number of pins that you need to use in order to perform parallel, to move the data in parallel. It is expensive in terms of the wires or the channels that you will need in order to move the data, because you will need a wire for every bits. Another disadvantage of parallel communication or parallel transfer is you can only use it for short distance. And this is obvious, because if you are dedicating one wire for each bit to be transferred, then you will need n wires for n bits to be transferred. And this is the cost of these wires or channels, communication channels, will be expensive as the number of bits increase. So you cannot, and the distance increase. So as the number of bits increases and the distance increases, the cost of these wires will increase. Another thing or factor that plays a role in the short distance problem is the interference between, or the cross interference between the wires. So if we have 8 wires that are transferring data from point A to point B, these wires will cross-talk, will interfere with each other. The data on each wires will interfere with other bits that are being transferred. So this is a problem, and it becomes more problematic when the length of the wires increases, because as the length increases, the coupling between the wires increases. So in other words, the interference between the wires increases. So this is a problem with parallel communication. The cost of the channels or the wires, the interference that may occur, which forces the distance of communication to be short. Now, how can we overcome these problems? Let's say the cost of wires, the number of pins that we need to dedicate or use from the microcontroller for communication. How can we communicate over a longer distance? Basically, this is dealt with using the serial communication. And in serial communication, basically, serial means one at a time, one after another. We send the 8 bits that we need to transfer, let's say, for example, from point A to point B, from the microcontroller to some other device, or vice versa, one bit at a time, one bit after another, and hence the name serial. So the bits are transferred one after another on the same wire. So we only have one wire that is shared between all the bits. So we send the first bit, then the second bit, the third bit, the fourth bit, one after another. Okay, and if we do this, we can reduce the problem of costs. We reduce the cost of the system because we are using one wire, we are using one interface or one pin, one interface or one pin to transfer the data. And because we have one wire, there is no cross talk, there is no cross interference between the multiple wires that are carrying data, because there is only one wire. So we can run for longer distances. So we can, if we do this, if we transfer the bits one after another, we can run for long and short distances. This will be cheap. However, this is slower than the parallel case because you need to finish the first bit in order to start transmitting the second bit, and then the third bit, and so on. So they are transmitted one after another. So it is slower. This is obvious. Also, this serial communication requires additional hardware to transmit and receive, and we will discuss this shortly. Because if you look at the data that is stored inside microcontrollers and CPUs and computer systems, usually they are stored in parallel format. And what do we mean by parallel format? Like every memory location has 8 bits, which represent, let's say, some value. And if you want to transfer this in parallel, you just take these 8 bits and put them on 8 wires or on 8 pins, and they are transmitted. So there is no problem. However, if you want to transmit these bits, which are 8 serially, then you need some mechanism to deassemble these bits and to be able to work with them one bit at a time, which we call the process of parallel to serial conversion. We want to convert the data representation from one unit, 8 bits together, to 1 bit at a time, which is called parallel to serial conversion. So these are basically the 2 approaches that are used to communicate data: parallel approach and the serial approach. The serial approach has advantages over the parallel. However, the parallel also has advantages over the serial. So it is a trade-off. It depends on it is a compromise between cost, interference, distance, and so on. Okay, so the serial communication basically is to transfer data from one point to another over a single channel or over a single wire. Okay, so if we have, this is the microcontroller. Let's say we have some other system here to which we want to transfer data serially. We want to transfer data serially. How to do that? Basically, we will send the bits one bit after another. For example, let's assume that the data that we have is 4 bits, which is 0, 1, 1, 0. This is the data to be transmitted from the microcontroller to the other end, to some other system, some remote system. So what will be done here? Usually there will be a pin that is used to output the data. So the microcontroller will output 0 first, then it will output 1, then it will output another 1, then it will output a 0, like this. So basically, this is how to do it. Now, if we look carefully, there are some issues related to this serial communication. There are some challenges. For example, here, how to know that this represents a single 1 or 2 ones or 3 ones or 4 ones. How to know if this low level represents 1 0 or 2 zeros or 3 zeros or 5 zeros? So there is a big challenge here. How to distinguish the start and end of each bit? How to distinguish the start and end of these bits? How to distinguish when the transmission starts and when the transmission of the data is over? For example, if I want to transform 4 bits, how do I know? How does the receiver here, the receiver, know if the transmission has started? How does the receiver know if the transmission is over? Okay, so these are 2 important challenges here, which are basically how to distinguish or how to know when the transmission starts. How to know the start and end of each bit. How determine the start and end of each word or frame, they call it. Word, yani the set of bits. The set of bits that we are transmitting or receiving, they call it word or frame. But we will make a little bit, we'll see a little bit difference between a word and a frame, but generally it is a word. How to know that? How to know when each bit start and end? Basically, there are 2 approaches, as it is shown on the slides. We have synchronous approach and the asynchronous approach, the synchronous and the asynchronous approach. So basically, how do I know if there is, when each bit starts and ends? Basically, I need some timing mechanism because I need to know the duration of each bit. So the most straightforward approach is basically to synchronize the transmission of these bits with another signal that is also transmitted to the receiver. So here we have the data that is transmitted. Here we have a clock that is used to synchronize the operation, the transmission process. And the purpose of this clock is basically to time the duration of each bit, to time when each bit starts and when each bit stops. So if I take this down here and I draw it, this is 1 like this. Usually, this is the data that is transmitted, and this is time. So this is the first bit that is transmitted. Usually, there is a clock, something like this. So every 1 cycle of the clock is basically 1 bit duration. So the bit starts from the falling edge and ends before the following falling edge. The same here. This bit starts here and ends here. This bit starts here and ends here, and so on. So we say here this is 1 0, this is 1, this is 1, and this is 1. So on every, let's say, falling edge, we are transmitting 1 bit. We are transmitting and receiving 1 bit. So the receiver now knows, for example, that on every rising edge, he needs to read 1 bit. For example, he needs to read 1 bit. So he reads 0, 1, he reads a 1, and here he reads 0. He reads a 0. So this is very straightforward. In order to know when each bit starts and ends, basically I need some measure of time, some time reference. So I will use a clock, and this clock has to be the same clock for both the transmitter and receiver in order to be synchronized, and hence the name of the approach, which is synchronous serial communication, which is synchronous serial communication. In other words, the transmission of the data is synchronized with the transmission of a clock signal, is synchronized with the transmission of the clock signal. Okay, so this is called synchronous communication. Now for the duration of the transmission, here using this clock, we know the duration of each bit. So we know the start and end of each bit. How about the duration or the how to determine the start and end of a word? Basically, there should be some agreement between the transmitter and the receiver that every word is 8 bits. So every 8 bits received, they will be considered to represent one word or one 8-bit value or one 4-bit value. It depends on the agreement between the transmitter and the receiver. Okay, so now let's assume that the clock cycle here, for example, is 1 millisecond. Is 1 millisecond. 1 millisecond. So this is the period. So every 1 millisecond, we are sending out 1 bit. So what is the transmission rate? At what rate we are transmitting data? We are transmitting 1 bit every 1 millisecond. So this is 1,000 bit per second. This is you don't see the board. So this is, if we assume that the period is 1 millisecond, 1 millisecond, did you see all this?
دكتور yes شكرا.
Okay. If I assume this is 1 millisecond, then the transfer rate or the transmission rate is 1 bit over 1 millisecond, so it is 1,000 bit per second. Or in our case, although it is not always the case, we will call it the baud rate. Okay, we will call it the baud rate. What is the baud rate? It is 1,000 bits per second, which is basically the speed at which, or the rate at which we are transmitting the data. So this is the synchronous serial communication, which is basically in which we are transmitting, we are using a clock for timing, and this clock is common. It is the same clock between the transmitter and the receiver, and how to have it common, basically it is sent in parallel with the data. So in synchronous serial communication, we are not technically using one wire, we are using 2 wires, one for data and other for the clock. And basically, each clock cycle represents 1 bit duration. Okay, so okay, let me go back. So this is the synchronous serial communication. It reduces the cost of the parallel communication because the number of data wires is independent, basically, of the number of bits that we are transmitting, which is the case for the parallel communication. However, we need another wire. So this might not be used over long distances because there will be a crosstalk between data and the clock. However, there is a reduction in cost in terms of the wires, the number of pins, and the interface circuit that I have here and here in order to perform the communication. So there is a reduction in cost, but this might not run for very long distances because there will be interference between these two, and the cost of the channels, and because these channels, these wires might not be actually copper wire, they might be fiber optic channels, they might be wireless channel, so they might be expensive to use. Okay, now how to address this issue, which is we are still using in synchronous, we are still using 2 wires. So we can't run for longer distances. We can't, the cost might be higher. Basically, we need to go back to the square number one, where we are transmitting the data serially, one bit after another. So we technically need one channel. And this is the idea of the asynchronous serial communication, in which the transmission of the data is not synchronized with the transmission of a clock. However, there is a clock. We still need a clock in serial communication, because we need to know the duration of the bits. We need to know the duration of the frame or the word. However, in asynchronous, we don't transmit the data, but the clock, but we use a clock. We have to use a clock. The timing is derived from the data itself. The timing is derived from the data itself. And basically, I will explain it on the board very quickly. So in asynchronous communication, we try to remove the transmission of the clock. We try to avoid the transmission of the clock. So basically what happens is we have usually the transmitter. It could be a microcontroller, it could be whatever, anything else. We have the receiver here. So what we will do, we will have the data, our data, which could be 4-bit, 8-bit, 2 bits, whatever, which is stored in some register. We will start to send the bits in this register out on a single wire, and this data should be received on the other end and stored in some register. However, how do we know the start and the duration of the bits? How do we know the duration of the frame or the word? We need some clock. So what we will assume here is that there is a clock at both ends. There is a clock here, and there is a clock here. And we will assume that both the clock are exactly the same in terms of frequency. They have the same frequency exactly. And this clock is used to send or to time the transmission of the bits here, and it will be used to time the reception of the bits here. Okay, so if we assume that they are of the same frequency, do we need to transmit the clock? We don't need to transmit the clock because we are running at the same frequency. However, there is a problem. There is still a problem here for the clock. We don't want to transmit the clock because we don't want to use a separate wire for the clock. So we are running at the same frequency, exactly at the same frequency. But there is a problem here. Even if we are running at the same frequency, there is a little problem in transmitting and receiving the data. What is the problem? يلا يا يزن مش يزن يزن.
غير ال starting وال ending.
بغض النظر, and now I have two clocks that are running at the same frequency, so I can time the bits at the receiver, I can time the bits at the transmitter. However, there is a very little problem here.
يمكن ما يكونوا synchronized مع بعض the two clocks.
Exactly. This is the point. The clocks themselves, despite being of the same frequency, they most probably they will not be synchronized. For example, the transmitter clock, for example, it is turned on at this moment. So it is running like this. So this is the transmitter clock. However, the receiver clock, it might be turned on here. So this is not working. There might be a lag or a time difference. So this was started here and this was started here. So there is a lag in the two clocks. In other words, as Jason said, they are not synchronized. So we need to find a mechanism to synchronize the clocks in order to transmit and receive the data correctly. And what is this? How is this achieved? Basically, it is written here. The timing is derived from the data itself. This does not mean that the clock is inside the data. This means that there are some hints, there is some information about the timing of the clocks inside the data itself. So basically what we will do is this line, this communication line is usually set to some default value if there is no data being transmitted. If there is no data being transmitted, then this line is usually set to some value. In other words, when the line is idle, this is the word that is used. When the line is idle, it is usually set to some default value. And it depends on the communication protocol. This default value could be logic high or it could be logic 0. There are only two values. So let's say this is the line. I will draw some timing diagram here. So let's take the same case, or yeah, it doesn't matter. This is the voltage of the line. So when the line is idle, the voltage on the line is set to high, okay? When the transmitter wants to start the transmission, it will notify the receiver, that it will start the transmission by changing the value of the line. So the receiver, when it sees the first falling edge, in this case, in this example, the first falling edge on the line, it will turn on its clock, because this implies that the transmitter has turned on its clock. So this information basically is used to synchronize the two sides, the receiver, the transmitter, and the receiver. So what the transmitter will do usually is will bring the line to the opposite state, and in this case, it will make it 0 for at least 1 bit. Then it will start transmitting the data. And our data was 4 bits, for example. This is the second bit, the fourth bit, like this. Let me just make it to scale. So this is, the transmitter will keep or will force the line to the opposite state to indicate the start of the transmission. Then it will start transmitting the data. So this is the first bit, the second bit, the third bit, the fourth bit, like this. So what the transmitter did is basically change the state of the transmission line or the communication channel from the idle value to the opposite value. So, and it will keep the line in this state for at least 1 bit duration. So that's why this bit is not part of the data to be transmitted. It is a control information, a timing information inside the data itself. So that's why it is called the start bit. This is the start bit, which is 1 bit duration that has a value opposite to the idle state. Now, what comes next is 0, which is the first bit, the second bit, the third bit, the fourth bit. Okay, now how does the other end know if the data is over? Basically, there should be some agreement. Like the data size is 4 bits in addition to start bit. So usually the start bit is not counted as part of the data. It is control information. Okay, so suppose that we transmitted this. What will happen next? The transmitter will put back the line to idle state for at least 1 bit. We'll put it back in the idle state for at least 1 bit duration, and this is not part of the data, but it has to bring the line back to idle state before it starts another transmission in order to keep the clocks synchronized. So if it wants to start the transmission, it will bring this back here to start bit, and so on, it will start the transmission. So that's why this bit is a must. It is called the stop bit. This is in the asynchronous serial communication protocols in general. Now, if you go to different protocols, you may find that the protocol states that the start bit has to be 2 bits. The duration of the start state has to be 2 bits or 3 bits. The stop bit time is a 3-bit time, or the stop period is basically 3-bit time. So basically, this is how it is done. In asynchronous communication, we have the transmitter and the receiver running at the same frequency. Technically, or ideally, these frequencies has to be of exactly the same. However, in different protocols, they can be within some certain tolerance. For example, this can be F plus minus some delta, F plus minus some delta. And this tolerance basically guarantee that the 2 clocks will be synchronized. There will be no significant lag between the 2 clocks such that the data is received correctly. Okay, so this is basically the idea of asynchronous communication. Asynchronous does not imply that there is no time, there is no clock. There is a clock, but asynchronous implies that there is no synchronous transmission for the data and the clock. We don't transmit the data, the clock synchronously with the data. What is the advantage of this? We are only using one channel or one wire. So we have only one interface circuit here, There is no cross interference, only one wire. This can run for long distance because only one wire, and in terms of interference, we have no self-interference or cross interference between the data and the clock, and so on. All right, so this is the basic concept of asynchronous serial communication. So this is time. Now, in the terminology of asynchronous communication, or in communication, this is basically my data. This is basically my data. This is my word. This is my word of data, which is 0111. And this is included when we talk about the data and the start bit and the stop bit, we are talking about a frame. So this is the difference between a frame and a word. Word, basically, it is the raw data, my data, and the frame is basically the data in addition to any control bits that I added to the data in order to control the transmission process. All right, okay. Now, any questions?
دكتور الستوب بت هاي بعد ما تخلص السيجنال ولا بعد كل بايت او بعد كل وورد؟
بعد كل word. يعني for every frame, if I want to transmit 8 frames, راح يكون في عندي 8 stop bits و 8 start bits. كل word راح يكون في لها stop bit و start bit. او اكثر حسب البروتوكول.
اوكي، يعني اللي بحدد بينات الموضوع البيتس اللي هو البروتوكول بيكونوا
يعني بعض البروتوكولز بحكي لك الستارت بت لازم يكون مدته 2 بت تايم، يعني لازم يكون 2 بت تايم هالقد. يعني الترانسميتر لازم يخلي اللاين لو فور 2 سايكلز، خلينا نحكي.
يس
اوكي تمام. Okay, one important thing related to serial communication in general, not specifically to asynchronous, is what happens here. As we said, usually the data inside digital systems is stored in parallel formats. In other words, the bits are, or a certain number of bits represent some value, and they are processed as one unit. However, when we want to perform serial communication, we are transmitting the bits one after another. In other words, we need to break, let's say, the 8-bit unit into 1-bit units. And how to do that? Basically, we need to perform what we call the operation that is parallel to serial. Usually, we have here a register that we call a shift register, in which we load our data. And every one of us knows what is a shift register. Basically, it is a register where you can store data and you can shift it to the right or shift it to the left. You can shift the data in or you can shift the data out of it. So basically, in order to perform this operation, the data is usually some value in memory that is 1 unit, 1 n-bit unit. How to break it into its individual bits? Basically, we use a shift register. We use a shift register to perform this operation. We convert the data from the parallel format into serial format. In other words, 1 bit at a time. On the other side, basically, we also need a shift register to shift the bits in. And once the word has been received, we move it to, let's say, to memory, or we move it to some register inside the CPU. So here we have serial to parallel conversion. We receive the bits, we collect them in a shift register that shifts the data in. And once we have received all the bits, and as we said, the number of bits has to be agreed upon between the two sides, we send the data, or we can read the data in parallel. So at the transmitter, we have parallel to serial conversion, and at this side, we have serial to parallel. And both operations are done basically using a shift register. A register which you can load the data in, and then you trigger, or then you clock the register to shift the data out 1 bit at a time. The opposite happens here. The data is shifted into the register, and once the register is full, 8 bits, 4 bits, depending on the word size, it is read in parallel to convert the data into the parallel format that is used by the receiver. Okay, so these are the basic concepts. Start bit, stop bit, word, frame, 2 frequencies, 2 clocks, they are not transmitted, the conversion from parallel to serial, serial to parallel. All of these concepts are used and will be detailed when it comes to talking about the SCI module or device inside the HCS12 microcontroller. All right, so here we have another slide which shows the difference between synchronous and asynchronous, and basically the difference is in transmitting the clock. This we talked about, which is in any serial communication process between 2 digital systems, we need a shift register in order to shift the data in and out and convert it from parallel to serial and then from serial to parallel. And to do that, basically, we need a clock, because on every cycle, we shift the data out by 1 bit, or we shift the data in by 1 bit every cycle at the receiver side. This is about synchronous serial communication. I will not talk in details about it. Chapter 11 talks about the SPI protocol, the serial peripheral interface protocol, which is a popular example on synchronous serial communication protocol. Basically, there is one link to transmit the data, and there is another link to transmit the clock. Now, the clock, as in this figure, could be coming to both node 1 and node 2 from some external source, or it could be basically generated by one of the nodes. And in this case, if one of the nodes is generating the clock, we call it the master node, while the node that is receiving the clock is called the slave. And the idea here, this node is called the master node because it has the clock. It has the heart or the beat of the system. If it kills the clock, there is no communication. That's why it is a master. So it controls this node and the communication with this node. So if you are interested about this, chapter 11 or 10 talks about the serial peripheral interface protocol, which is basically a synchronous serial communication protocol. In concept, it is similar to what I discussed on the board. There is a clock transmitted in order to do the time. This is a timing diagram similar to what I had on the board. As we said, the synchronous serial communication requires simple hardware. You can run at high speed. Disadvantages, you need an extra line for the clock. And the clock and the data may lose synchronization over long distances. That's why most synchronous protocols are only specified for short distances. Asynchronous communication, as we said, there is no clock. However, the transmitter and the receiver, there is no clock signal that is transmitted. However, both sides are operating a clock at the same rate. To synchronize the clocks, we use a start and stop bits. And this is, as we discussed earlier, I will leave this. But the idea here is very simple, that usually the transmitter is running at a frequency F, let's say F. The receiver is also running at frequency F. But technically, the receiver is usually running a faster clock in order to collect multiple samples per bit. And why is that? Basically, the receiver does not want to rely on one point to determine the value of the bit. Okay, so it usually runs a faster clock to read the value of each bit, but the bits are shifted into the register at the same rate at which they are being transmitted. So basically, there is a sampling clock that is n times the shifting clock, and this clock basically has the idea of taking multiple samples. You take a sample here, sample here, sample here, sample here, sample here, then you decide on the value of the bit based on the majority of the values, that you have for the samples. For example, here we have 0, 0, 0. There might be some noise, for example, here like this. So this will be read at 1, but the remaining samples will be 0. So the receiver will decide that the bit value is 0 because most of the samples are zeros. So for example, here, the receiver is running X times 16 clock. What is this? Basically, the receiver has a faster clock that is 16 times faster in order to take multiple samples per bit, not only for the start bit. This is just a demonstration. For every bit, at every rising edge or falling edge, the receiver takes a sample from the bit, okay? And once it's over, this time is over, it will specify the value of the bit as the majority value of the collected samples. And this value will be shifted into the shift register at the receiver at a rate that is similar to the transmission rate. So this is for just sampling. Okay, so this is usually implemented in all protocols just to make sure, or to reduce the probability, or to reduce the effect actually of interference. For example, as we said, assume this is the start bit, which has to be 0 for 1 bit duration, which is, this is the, let me draw it using this. So this is 1 clock period, 1 clock cycle for transmission and reception. However, the receiver is running also a faster clock to collect samples. So assume, for example, we have some interference here, this like this. So it changed the start bit for some duration. So the samples collected here and here, we will take the majority of the value. So it will be 0. So this is very important actually. This is very important because, for example, if you have if this is the line which is idle, so the line is idle, and the receiver is supposed to see the line idle if there is no transmission. However, suppose that there was some interference that forced the line to behave like this. Or this is not very practical, like this. So the line went low for a very short period of time. So the receiver will observe this falling edge, and it will think that there is a transmission that is about to begin. So it will start its clock and will start shifting the data. This bit, so it will read all once. However, there was no transmission. So how to reduce this problem is basically not to rely only on the falling edge. The falling edge will trigger the receiver to start taking samples, let's say 16 samples, and then decide whether these samples are, the majority of these samples is 0. So there is a start bit. So this is very important. And the same idea or advantage or benefit when it comes to reading the values of the data bits that I'm transmitting. There could be some sort of interference. So this is the line idle, it went low, this is the start bit, and this is 0, this is 0, for example, this is 1, and so on. Now, if I only take one sample per bit, let's say at the middle of the bit, there might be a problem if this bit is essentially 0, but for some reason it went like this. So my sample will have, I will read error, but if I take multiple samples per bit, I will reduce such problems. That's why this is, as I said, very common in serial communication protocols, especially for the asynchronous, because they run for longer distances. The external interference, the probability of external interference is higher. That's why most asynchronous protocols, they have this multiple samples per bit in order to decide on the value of the bit. All right. Any question? طيب, I will stop here. يعني we took an idea about serial communications, the forms of serial communications, advantages, disadvantages, and so on. Next time we will look at the SCI module that is available in HCS12 microcontrollers. We will talk about some of the features. There are a lot of features and functionalities related to this module. There are different modes of operations. We will take the basic modes of operations in order to demonstrate the idea. All right. So, but as I said, you will see next time that we now know what is meant by serial communication, asynchronous serial communication. So we need just to know what are the registers that are related to this module inside the microcontroller, what are the supported features, and so on. So it will be very simple and straightforward.
مرحبا دكتور، بصير اسال بس؟
تفضل.
دكتور، بخصوص البود ريت، البود ريت بكون يعني انا بعرف، يعني شفت كثير مثلا بشوف مثلا كثير رقم 9600 مثلا.
نعم.
اوكي، هلا هاي يعني هذول بيكونوا within ستاندرد معين، يعني هذول الارقام، او اشمعنى هذول الارقام يعني؟
هلا في مجموعه من الارقام هم ستاندرد، يس، او متعارف عليهم، بلاش ستاندرد، متعارف عليهم.
يس. بس هذول يعني لازم يكون البود ريت بيشتغل، يعني لازم تكون الفريكونسي تبعت الكنترولر اعلى من البود ريت اللي بيعمل فيه، صح؟ اللي بيشتغل عليه، صح؟
فريكونسي تبعت الكنترولر كيف؟ what do you mean؟
يعني مش احنا حكينا انه انا باخذ باول شيء لما كنا نشرح على السينكرونس كنا نحكي انه لما اجينا نحسب التايم او لما حكينا على فريكونسي انها هي 1 ملي سكند التايم بيريد، فانا اذا بدي بود ريت اعلى لازم الكنترولر تبعي يكون اوريدي
لازم اغير الفريكونسي اكيد.
اوكي يس، بس يعني عشان هيك لازم تكون الفريكونسي اوريدي تبعت الكنترولر اعلى من البود ريت، رايت؟
Yeah, that's what happens actually. راح نشوف next time كيف كانت الفكره بالاي تو دي كونفرتر. هلا بالاي تو دي كونفرتر الكلوك تبعت الاي تو دي هي ديرايفد من الاي كلوك، مضبوط؟ وبعد بس لكن الماكسيمم تبعها 2 ميجا هرتز، صح؟
يس.
فكيف كنت اقدر اسوي ديرايف للكلوك من تبعت الاي تو دي من الاي كلوك؟ عندي يعني مالتيبلاير معين بريجستر معين بقدر احدده حتى اغير له. وهون نفس الفكره. الاس سي اي موديول رح نشوفه المره الجاي بيكون داخل عليها الاي كلوك، وهي الاي كلوك اللي هي نص المين فريكونسي، مضبوط؟ الاوسيليتر فريكونسي بقدر اسوي لها سكيل داون حتى اشتغل على بود ريتس مختلفه.
اوكي يس تمام.
تمام؟ alright. اوكي. اوكي. other questions. طيب هلا انا اللي عم بفكر فيه بصراحه يعني بالنسبه للهوم وركس والكويزز، احنا سو فار اخذنا 2 هوم وركس، اخذنا 2 كويزز.